Hello everyone, this is Akshay. I'm Akshay Gawal and I would be presenting the paper on estimating POS annotation consistency of different tree banks in a language. So let's get started. First we start with the motivation and the measure definition. So the main motivation is that there are multiple annotation guidelines for different tree banks in the same language even. So for example, in English there would be an example of Venn tree bank, taxit, there is universal POS taxit, and so on and so forth. Now, given that there are multiple different annotation guidelines, if comparing the different tree banks in a particular language within the same annotation guideline, how do we check if the tree banks are annotated consistently with respect to each other and with respect to the annotation guidelines? With respect to annotation guidelines is fairly simpler, but with respect to each other, that's where the problem comes in. Now, there have been some approaches to solve this problem. The first one being the training tagger and parser on one tree bank and notice the drop in parser scores over the other. It was first used for Spanish tree banks by Martinez Alonso and Zeman. However, one of the bottlenecks is the performance of the use model. So if the model learns very poorly, then is it a feature of the parser scores, or is it a drop in the scores? Then secondly, the architecture of the trained model. When the architecture is changed, then the drop, let's say from 10%, a drop of 10% suddenly is catastrophic in one particular architecture, but in the other architecture it's not as catastrophic. So depending on the architecture of the trained model, that also matters. Now, the second approach being the variation nucleus method as proposed by Dickinson and Morris. This is the most famous one, and it compares the peer annotation in n-grams. However, the degree to which different tree banks differ from each other has not been fully solved. We start with the definition of the Kullback-Leibler divergence, which measures how different is one probability distribution from the another. Extending the Kullback-Leibler divergence, Rosen-Zabokertsky proposed KLC-PS3 measure, where they tried to measure how much distribution of coarse POS trigrams differs in two different tree banks, with the distribution of a POS trigram being given by the formula below. FCPOS3 as the count of trigram was divided by the sum of the count of all the trigrams in the tree bank. In this paper itself, so Rosen-Zabokertsky showed that this measure KLC-PS3 can be effectively used for source selection in a delexicalized cross-language parser transfer scenario. So tree banks chosen in the POS annotation distribution, they are a better fit for source transfer to another language than those that have POS annotation more further apart. We extrapolate on the same idea, saying that if the true tree banks have a POS annotation distribution of POS annotation close by, then we say that they are being annotated consistently, otherwise they are inconsistent in the annotation. Since KLC-PS3 and Kullback-Leibler is also a divergent metric and it's not symmetric, we propose a symmetric variant where we go from A to B as well as B to A, and we call this sum as theta POS of A and B, and this is limited by a threshold or an estimated empirical upper bound called capital theta POS. It's not a upper bound on the scores that theta POS can take. It's a score based on how much we want to assign, saying that okay, now the tree banks are consistent, now the tree banks are not consistent. Let's look at the dataset. We perform the experiments on UD version 2.5 tree banks, which contains 157 tree banks in 90 languages. Some languages contain up to 5 tree banks, and UD is a perfect playground for this proposed measure because multiple tree banks annotated or re-annotated as per the same annotation guideline, which is one of our primary concerns. The second thing is there are multiple languages, and so the measure can be developed to be non-language centric or even language family centric. UD also provides an internal ranking of the individual tree banks, which is an assessment of the tree bank's compliance with the guideline. Now, if a tree bank complies to the guidelines better than the other tree bank, we also say that we can say that it's fairly consistent by itself, and that's what we use as a filtering criteria for selecting high quality tree banks, where we select 3.5 star rating tree banks with rating of 3.5 stars or more out of the 5-star rating. While working with data, we have two main assumptions. The first one is the tree bank is internally consistent in its annotation. So the different parts of tree bank, they're all consistent with each other, but this might be a strict constraint when it comes to tree banks with multiple genres. And so we assume that if the tree bank consists of genre 1, genre 2, genre 3, then individual genre 1, genre 2, and genre 3 would be consistent themselves. If it's possible that the tree bank itself is not consistent, but the individual genres would be consistent overall. We first estimate how the size of the database how the size of the dataset influences the theta POS measure. Over here, if we look at over here, if we look at the sentence, this shows the growth of POS diagrams, the number of distinct POS diagrams in red, and the total number of POS diagrams in blue. And we can see that the curve is similar across both languages. This one is for Estonian EDT and this one is for Czech PDT, and we notice that this is pretty much the similar curve, but we notice that somewhere around initially, when we zoom into the part up to 2000 sentences, we notice that 40% of the unique POS diagrams are present only somewhere around 400 sentences. So if a data set contains less than 400 sentences, then that means it does not even represent the full scope of the POS diagrams that it can achieve, and so we would be using that as one of the constraints. The second one is the difference in the average length. So consider the Arabic NYUAD and the PUD tree banks. The difference in the average sentence length is almost by a factor of 2. So which means more trigrams. If we take the equal number of sentences, then NYUAD would have more number of syntactic words and more number of POS diagrams, which effectively plays against Arabic PUD. So that's another caveat we need to take into consideration. So how do we take them into consideration? The first one is really simple. We make sure that the individual data set has at least 400 sentences. So if tree bank A and tree bank B are being compared, we establish that both of them have the size in terms of the number of sentences as more than 400. Now coming back to the problem of average sentence length, let's say average sentence length of B is less than the average sentence length of A. Then in that case, we would require that the total syntactic words in dataset B is more than or equal to 400 times the average sentence length in A. This makes sure that there is no bias when it comes to the size of the sentences, and we have almost a comparable number of total POS diagrams. The experimental setup required a large number of sentences in a single genre, so we isolated the news genre, and we selected tree banks with high star rating, as mentioned before, and from different language families. So we used Czech PDT, which is Indo-European and 4.5 stars, and Estonian EDT, which is Uralic and 4 stars rated. The experimental process downsample the data from either tree bank. This is an optional step, and we run k-fold cross-validation, and the downsampling was just so that the k-fold could split the tree bank into equal chunks. Otherwise there's no need for it. We report the average score of the cross-validation runs and then compare and then check the behavior of the theta POS limits. We found that for tree banks containing data from same genre but differing only with respect to the size of data, the theta POS of A and B was at a maximum value of 0.5. So in this case, when capital theta POS would be 0.5 when the data differs only with respect to the size and not with respect to the genre. When it comes to genre distribution and the variability of theta POS, there are some caveats related to it. So for example, in the figure we see the GA represents the dataset X can be split into constituent genres, such that GX is a collection of genres in the tree bank. So over here we notice that this can play out in either of the three ways. One, where GA is a subset of GB. Case 2, where it's not a subset but they are intersecting. And the third one, where they are when they are both non-intersecting and disjoint sets. Now when we talk about genre, then there is another additional thing where chemistry and physics, for example, they are different sources. So in one annotation guideline they can be kept separate, or in the another annotation guideline they could be clubbed under the umbrella category of science. So how do we separate the two? Plus, multi-genre classification of data is also possible. For example, if data is being borrowed from a physics-based forum or from Stack Overflow, for example, then it would be blog plus the subject matter where it comes from. So would it be classified as physics or blog? Not sure. Combine it as both physics and blog. That's how the annotation guidelines might define the genre as. So we previously estimated some heuristics constraints, but if a set of genres do not stick to those constraints, like so genre X does not have 400 sentences and it's really less average sentence length, then we denote that set of genres by adulterant genres dataset, and we call it as G adulterant. And of course it might not always be possible to split the dataset into its constituent genres. For the experimental setup, we required a large number of sentences in multiple genres, and we selected Treebanks with high star rating from different language families. For this one, we use Polish LFG, Indo-European 4 stars, and Finnish TDT Treebanks, Uralic and 3.5 stars. Again, we downsample the data from individual genres in a given tree bank. Optional step. Then this one is not optional, because over here we want to make sure that the size differences, there's no size difference. So with the size difference not coming in, we have to focus on just the genre. Now we study interaction of genres starting from 1:n. So one has just one genre, the other part has one genre, two genres, three genres, so on and so forth, going on to M:2n setup where multiple genres on both ends. We report the theta POS scores on each interaction and then compare the bases. Now when over here the theta POS AX and BY, where AX represents genre X in dataset A, we notice that this has a maximum cap of 2.0, and this is the upper bound that we set in individual genres. But when it comes to multiple genres and a combination, then we switch to the formula over here, which specifies that the average of the calculated theta POS scores plus 2.0 if there's an adulterant genre, or if there's no adulterant genre, then we just go by the average theta POS scores. We have so far studied the effect of when genres are same and when genres are different. So we have the theta POS of AX and BY as 0.5 or 2.0. We can average the scores, but it's not always useful. Let's assume a case where AX and BX is 2, AY and BX is 2.2. Both are upper limits, by the way, and the calculated theta POS of the Treebanks is 2.5. Now the average would be 2.1, which is less than 2.5. So average of 2 and 2.2 would be 2.1, which is less than 2.5. And so we would be saying that the Treebanks are consistent, even though in even though this might not be the case. So to combat this, we use a theta POS for each genre, where we identify theta dash POS as the average of theta POS AX and BY, capital theta POS of AX and BY, where capital theta POS is 0.5 or 2.0. Now, when we have to combine the different genres, AX, BY, depending on whether, doesn't matter if they might be same or not, we use the minimum of this calculated theta dash POS as well as the average theta POS and 2.0. So 2.0 is limit, so that when X is not equal to Y, then we have 2.0. So average of 2.0, 2.0, 2.0, 2.0 would be 2.0, and that's when there are no adulterant genres. When there are adulterant genres, we add 2.0, and when there are no adulterant genres, we do not add this limit. For marking Treebanks in UDV 2.5 for inconsistency, the red shows the inconsistent, green shows consistent, and some of the Treebanks could not be estimated because they could not be split into. We decided not to give a biased view of saying that they are annotated or they are consistent or not consistent, so we gave them as gray, as could not be estimated. And this is also the capital theta POS scores. These are also present in the paper in the appendix. For the working example, we show the two Treebanks in Latin, so ITTB and ProEL. ITTB has non-fiction and ProEL has non-fiction and Bible. The calculated theta POS scores for ITTB non-fiction and Bible was 3.702, which is more than 2.0 limit. The non-fiction and non-fiction was 3.558, which is more than 0.5. And this is the calculated theta POS for the entire Treebanks. For calculating capital theta POS, we have the average theta POS will be average of 3.702 and 3.558, which will be 3.63. The theta dash capital theta dash POS would be the average of 0.5 and 2.0, and that will be 1.25. No adulterant genres, so we calculate the overall capital theta POS as the minimum of 3.63, 1.25 and 2.0, which would be 1.25. Now the calculated theta POS score was 3.763, which is considerably greater than the upper bound of 1.25. Therefore, the pair of Treebanks is inconsistent in their POS annotation. To further show that the Treebanks are inconsistent in their annotation, we have the top 10 POS diagrams in the 3 Latin diagrams, in the 3 Latin Treebanks. I'm sorry. Over here, we notice that while ITTB and Perseus has punctuation marks, punct is the POS for punctuation, has the punctuation as the present in the top 10. There are no punctuation marks being present in the ProEL's top 10 trigrams, and the reason for this is that the ProEL Treebank has removed all the punctuation marks. This is one proof. The other proof is when we use variation nucleus method of Dickinson and Moyers, we saw that the two Treebanks differ in how they annotate hawk. So ProEL Treebank annotates it as adjective, while the ITTB Treebanks annotates it as a pronoun. So in conclusion, we propose a measure to judge POS annotation consistency between different Treebanks that belong to the same language and which are annotated under the same guideline. The measure can be extended to any given guideline and it's independent of the tagger performance, since there is no tagger being used. It's not being affected by the language typology or its family either, because we are comparing Treebanks of the same language. We can also use it to localize points of consistency in conjunction with techniques such as Dickinson and Moyers, like in the previous example, and the localization is possible both inter and intra Treebanks. To see this, for example, assume this part was within the limit of 0.5, then while we are generating the capital theta POS, we would see that this part is more than 2.0 and this part is consistent, but this part of non-fiction and Bible is inconsistent, and so that would be a problem. And this is it. Thank you.